Yeah. Should I start? Okay. Yeah, I don't know. Yeah, probably.
Okay, so it's a great pleasure to introduce our the speaker for the third set of lectures, Professor P.K. Mohanty from ISER Kolkata, and he'll talk about matrix product methods in statistics.
Okay. Good afternoon, and hope you are enjoying the school. So I'll be talking about a method to solve problems, some problems at least, and I will give you some examples about in non-equilibrium steady states, how to get exact solution of non-equilibrium steady states. Okay, so the task will be I'll define some models and try to solve them. This morning I have sent you this PDF file, which contains about 10 problems. So you know that during the end of these 5 lectures, I will solve some of these problems for you, and some of the problems I will not solve. You give you some hints so that you can solve it at home and privately, because there's a lot of algebra. Okay, so it will be mathematically a little bit of taxing, so we'll leave it to you doing privately. Okay, so look at these problems, and I insist that you read these problems, because I thought that if I define the problems, then you at least know that what you are going to solve. The problem might be interesting to you, may not be interesting to you. If it is not interesting, leave it. But if it is interesting, you should know how to solve them. Okay? Okay, and if those problems which you know how to solve it, don't try them, and only those which you think that it cannot be solved, at least try getting a solutions. Okay. So before I start my lecture, I would like to ask how many of you, just raise your hand if you have not done solution of one-dimensional Ising model on a ring, 1D Ising model exact solutions. Anybody who has not done it? I mean, there is nothing, if you tell me, then I will try to little bit elaborate on that. You have not done it. Anyone else? Exact solution of 1D Ising model. Okay, so I will start with that 1D, one-dimensional Ising model, exact solutions, and that is already, you know it, it's already there. Matrix product answers, which is a method which I'm going to tell, that is not needed. So you know the solution in another way, and what I'm going to tell you that you can also get it from matrix product answers. Okay, so the outline of my course will be this. Okay, so first thing is that introduction. I will just introduction. So here I will talk about equilibrium detail balance, equilibrium detailed balance, and Ising model and its dynamics of the Ising model. Okay, and then I talk of non-equilibrium steady state, states, and matrix product answers to solve them. Matrix product MPA, matrix product answers to solve for the steady state. Okay, and then and MPA, and also I will talk about MPA for open systems. Okay, this is one part, and then there is a part 2. So part 2, I will talk about some interesting models, which with some physical. Let me say them. So matrix product states, MPA, some examples. I believe interesting. Okay, so the first example I will take is two species particles, let us say two particles. So, okay, in this two particle thing, I will talk about there are two different particles on a ring, let us say, and one particle diffuses on the ring, the other one drifts, which means that the second one tries to generate a current in the problem, and thereby this coupled system will have a current, and what is the current in this problem. So, what we will see in a very interesting stuff called NDM, what you call negative differential mobility, which means that you can have, in this situation, you can generate negative conductance, right? I mean, generally when you increase potential, current goes up. Here you can get, like, if you, this is under non-equilibrium situations, you can have, like, you increase the potential, the current goes down. So you push more, it goes less. Okay, so this is one example which I take, and another example is that extended objects. Extended objects on a lattice. So all these methods are generally useful in one dimension. So all these models are one dimension, either on a ring, or 1D lattice, either on a ring or on an open system. Okay, so we'll discuss them, but extended objects, like one example is dimer, drifting dimers. Okay, so you have dimers, and on a ring, there are dimers basically mean the two which occupy two sides on a lattice side, and these ones are drifting, which means that you can go to right with some rate different from left. Okay, so in this case, we want to find out how does the correlation function looks like. Okay, so this can be solved exactly. So drifting dimers. Third example I will take is absorbing phase transitions. Okay, so like problems like Ising model or a driven system also, the ergodicity is something which is kept intact. Okay, so that helps us solving the problems. And when the system is absorbing, there are new features which comes up into the absorbing. Basically means that in some parameterism, with time, the system actually stops. Nothing happens in the system. Okay, and then if you change the parameter, suddenly some part become active. It's like COVID. Like, it's dead, and then sometimes it is alive. Okay, so this is also modeled by this absorbing state phase transitions, like, percolation. And, okay, and I will also talk about run and tumble active matters, which is a very fascinating topic currently. And so I will talk about two run and tumble particles. Tumble particles. Okay, so basically I will solve it for at least two particles, two run and tumble particles in the ring. Okay, so how to get an exact solution. So these are the two parts, and then third one I will go to open systems. Okay, so open systems so open basically means that the system which is boundaries, and from the boundary something enters into the system and some constituents goes out at the other end of the boundary. So these are open systems, and one of the system is TASEP, totally asymmetric simple exclusion process, TASEP, with open boundaries. Okay, so this is one, and then I will also talk about AHR model. Okay, I don't want to define the model now. These are many particle systems. Okay, and something called also Katz-Lebowitz-Spohn model. So I'll just shortly discuss about that, and then what? I think this is enough for here. Okay, and then finally I will go to 4, which is generalizations. Okay, so generalizations, which I will say that matrix product answers for systems in absence of hardcore interactions. And then second example is that MPA in 2D. Okay, so these are so these are the two things we talk about. And then the topic of this is other methods of solutions. Okay, other methods. So in other methods, like there is called pairwise balance. Let me write it. Pairwise balance. Because if you know the key, I don't know whether I can touch upon this, but at least if you know the words, you can look for it. Pairwise balance, H balance, and then bunch balance. Bethansas. Okay, so I do not know whether I can cover all these details. But at least for the keywords, I'm just giving the keywords. You can look for it later. Okay, so what I do, so how the lectures will be divided is that first one, these two will be 2.5, and this side will be 2.5. Okay, so this is a naturally thing. Yeah. Okay. So this is the way I will try to cover, and let us see that how much I can cover. Okay, questions at this stage? Okay. So what we do now is that very quickly I will try to do a solution of 1D Ising model, at least write it as a transfer matrix. Okay, so this much we do, and then we try to see that how this same solution can be obtained using matrix product answers. So when you talk of models, so I think Ising model in one dimension is the simplest model. So what do you mean by modeling? It's basically like, for modeling you need some space, right? I mean, where, and then you need some constituents, and you need how they interact. And given all this, you have to say what will happen to the system. That is kind of the thing. So when you talk of space, so you talk of continuous space or discrete space. Discrete space is a little easier in the sense that you can count them, like 20 lattice sides. It's not an infinity space. So lattice is a better option. The simplest, I'm saying that what is the simplest? That is lattice. Now, so let us say that there is 1D lattice. So lattice is like this. And you can define what are the variables. You should say what are the constituents of your model, right? I mean, so you can say that the constituents at each point has some variable called S. The lattice sites are defined I, and I plus 1, I minus 1, and the total is L sites. So this is the one, and if you have at each point I, you have a variable called Si. What do you want? How many variables you want for Si to be? The minimal is 2, because if you take Si equal to only one value called 1 or 7 or whatever, then there is no evolution. There is nothing interesting there, because if it is each value, each site, you can have only one value, there is only one configuration, so there is nothing interesting. The simplest is only two variables. You can call it plus minus 1 0 or A iron copper, zinc copper, call it whatever. Okay, so these are the variables. So Si can be one of the two variables. And now you have to say that given the variables, there are constituents, how they interact. That is given by a Hamiltonian, or it tells you the energy function. So basically how the...
Use the larger letters, larger font, right?
Oh, that is a little...
When we start formulas, please, just use it large.
Okay. So there is a site I, and the total site is L sites. Okay, and this is at each point you have a variable Si. Now I will take only plus 1 or minus 1. Okay, I call them spins. Okay. And the interactions, I just say that this is I minus 1, I plus 1, and the interaction is H equal to minus J. I'll put it J equal to 1. Why? Si plus 1. So I equal to 1 to L, and I have a periodic 1D periodic lattice. This is problem number 1. in this note which I've given. Okay? So 1D periodic lattice. So Si plus 1. So Si plus L equal to Si. Sorry, I. Si plus L equal to Si. So that's the periodic thing. And what does it mean? It just says that, there is some variables which is sitting there, sum of the product of the variables. That is your energy. So now for this model, if you want to write the partition function, I'll come here. Is it better? So let us write the partition function of the system. So because so partition function of the system is, I call it Z. So, okay, before that, so there is only one statement. What is very important in statistical mechanics is the probability of a configuration is proportional to e to the power minus beta energy of a configuration at a given temperature T, where beta equal to 1 by kT. Okay, so if you say this is Boltzmann's statement, as is already talked about it in the first lecture. So what you want to do is that if this is a probability, you want to normalize it. So that is you have to put a normalization constant. A normalization constant should be determined summation over C equal to 1. So n, basically n inverse equal to summation over configuration P of C. Okay. So if that is the one, then you can write probability of a configuration equal to e to the power minus beta E of C divided by summation over C e to the power minus beta E of C, and this one you call it the partition function. Okay, it's the inverse normalization constant to the probability. Okay, so what we do now is that we want to calculate this partition function, and the demand is that all thermodynamic variables can be obtained from the partition function. We'll see how. Okay. So the partition function Z equal to summation over configurations. And what is a configuration here? So if you specify all sides, that will take a configuration. For example, plus plus minus plus 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 minus plus, that's a configurations. How many configurations are there? 2 to the power L configurations. So there are 2 to the power L configurations. A configurations is denoted by summation Si. This I call a configuration. All spins specified. So as summation over configurations, I say that Si, all Si equal to plus minus. Right? Plus minus 1. And then e to the power minus beta E, I can write e to the power minus beta E is summation over I, Si plus 1. But minus beta, and there is a minus also here. In the Hamiltonian itself, there is a minus sign. So this will be e to the power plus beta Si plus 1. So this can be written as e to the power summation over S1, S2, all SL, and then e to the power S1, S2 beta times S1, S2 plus S1 plus S2, S3 plus S3, S4, and last one is SL, S1. But this, because it's in the exponential, you can take it out and you write it e to the power beta S2, S3 and e to the power beta S3, S4 like that. Okay? So then what you do is that this one, if you define as a function, then this is the same function. So you can call it some T S1, S2. If you call it T S1, S2, this will be directly T S2, S3. So this will be T S2, S3. Like that. And final one is T SL, S1. How many so okay. So I want to, so how many possible values this T can take? It's a function. S1 can, how many values? 4 values, right? S1 can be plus minus 1, S2 can be plus minus. So there are these values, and what is T plus plus? E to the power beta. Because by definition, T S1 S2 equal to e to the power beta S1 S2. So T plus plus is e to the power beta. Okay. So similarly, T minus minus is also e to the power beta, and T plus minus equal to e to the power minus beta equal to e to the power, T minus plus. Okay. So there are 4 variables, but you can write it in a matrix, no? I mean, no, because there are 4 variables, you can write it, this is T plus plus, as if plus and minus is your basis. T plus plus, T plus minus, T minus plus, T minus minus. Okay? And this definition, like T plus plus, I will just take T plus plus, is e to the power minus beta, e to the power beta. I will use a different notation. Okay, so I just said that T S1 S2 equal to S1 T S2. So basically in this notation, plus equal to 1 0 minus equal to 0 1. These are standard basis. You can write, if this is the matrix, so this matrix is T equal to this, equal to e to the power beta, e to the power minus beta, e to the power minus beta, e to the power beta. This is your T. Right? So now, so this is T, and so this is, if you plot plus plus, then you will get this, plus minus you get this, minus plus you get this. So this is the definition. Okay. So now a partition function, let us write the partition function, Z equal to summation over S1, summation over S2, summation over S3, summation over SL, each of them equal to plus and minus. And then the first term is plus, S1 T S2. This T S1 S2, that's by definition. T S1 S2 is S1 T S2. The next term, I will erase that. S1 T S2. The next term will be S2 T S3, like that, S3 T S4, like that. And the final one is T SL T S1. Okay. So now what I do is that, you know that if I use the standard basis, then there is a completeness relation. So that is SS summation over S equal to plus plus, plus minus minus equal to identity. You can multiply it here. Plus equal to this, so plus plus. So if you have plus plus, so which means that that is 1 0 times 1 0. So this is 1 0 0 0. So similarly minus minus equal to 0 0 0 1. So plus 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 minus minus equal to identity I2. Okay. So what I do now is that look at where S2 appears. S2 appears here. These two places S2 appears. And there is a sum over S2. So this one can be taken, it just can be taken. So summation over S2, 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 that is just identity. So similarly S3, S3, so I take out this and take out this sum and take out this becomes identity. So now finally S1, start with S1, end with S1, and in between there are L number of T's. So this will be equal to summation over S1, S1, T to the power L, S1. So if I make a sum, the T to the power L plus plus, plus T to the power L plus minus, that's called a trace. So this is equal to trace T to the power L, where T equal to e to the power beta, e to the power minus beta, e to the power minus beta, e to the power beta. Actually you can write it e to the power beta plus e to the power minus beta sigma x. Okay? Just because most people know it, I just did it a little fast, possibly. But still, if you have doubts, you can ask me. Why I did it here is that I wanted to calculate, given this, I want to calculate some expectation values. Let us say that I'll wait if you have a question. Okay, at this stage, let us say that I want to calculate the expectation value of S2. S2 expectation value. So what is the meaning of X2 expectation value? Because you have PC, which is P of Si. So S2 expectation value equal to P of Si times Si, S2 times S2, and summation over all S1, S2, SL, right? Divided by, this is SPS, by partition for P, whatever, this probability, okay? So if you write it like that, then what will happen is that you get a term. So this will be e to the power minus beta this divided by z. So this equal to 1 by z, this is the partition function, this z, and e to the power minus beta whole thing. And e to the power minus beta whole thing is just t s1, s2, s2, s3 like that, right? So what you get is that 1 by z, and summation over s1, s2, s3, t s1, s2, t s1, s2, sorry, I think I am still making it small. Okay, so this is 1 by z times summation over S1, S2, sorry, S1, S2, SL, and then you have to write your operator is S2, and then e to the power beta S1, S2, all of them. So that is just S1, T S2, S2, sorry, S2, T S3, like that, all of them. So in this sum, you can see, and then there is a S2 which is here, and S2 also is here. Now this S2, I'll put it here. Okay, so now you look at where does your S2 come? S2 sum comes over here, here, here. Right? So this sum will be different. Everything else you can take it away. So all of them will be T, but you have extra thing here. So what we'll have is that this S1 will make a trace. So let us write it, calculate this one for one time. Huh? This. Yes. Yeah, identity, yeah. I mean, if I don't write, that is identity, yeah. Okay. Constant means identity, yes. Okay, I2, yeah, formally, not only I2. Two-dimensional identity matrix is sitting there. Okay. So now let us look at what is this one. So I will not calculate this. I will call it numerator, n divided by z. So this equal to n divided by z, n equal to this. So n will be n here, and there will be S2 here, right? So what I have, so for S2 sum, I have to calculate it. So let us calculate that. Summation over S2, 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 or you can call it S, it's a dummy variable. S equal to plus minus. Okay, so this equal to plus minus, because when it is plus plus, this one S will be plus. When it is minus minus, this will be minus. So minus minus minus. And plus plus is just 1 0 0 1, which I wrote it earlier. 0 0. And minus is 1 0 0 minus 1. So this equal to 1 0 0 minus 1 equal to sigma z. Okay, so you get a sigma z there. So every time you want to calculate expectation value, that S variable will be replaced by sigma z. That's all will happen. Okay, so then what will happen? The n will be, this one will be sigma z. I'll erase that S2 sum and write a sigma z here. So now n equal to S1 t sigma z, because the second you are putting sigma z, and t, and everything else will go away. Okay, so now if you want to calculate S2 expectation value, so it comes out S2 expectation value equal to trace of t sigma z, this is 1t, and that is L minus 1 divided by trace of t to the power L. So this is 2, S2. What will be S3? T square. So S3 expectation value equal to trace of t square sigma z t to the power L minus 2. But this one is same as this one, no? Because because trace has a cyclic property. So what you can do is that t, you can take it here. So this is just trace of, first you write sigma z and t to the power L divided by trace of sig t at t to the power L. And this one is also the same, trace of sigma z t to the power L divided by trace of t to the power L. So, this is very natural, because wherever you calculate, expectation value has to be same, because it's on a ring, there is no special site on a ring, okay? But what is the magnetization value? So this is a S2 expectation value. Every site you have the same magnetization. S2 expectation value is magnetization, okay? And every place you have the same value, so you can multiply by L, divide by L, so you have a, it's an extensive quantity. Okay, so sigma z t to the power L is what? Sigma z equal to, you know that sigma z is plus 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 minus minus. So let us calculate that. So you have sigma z t to the power L trace. This is what you want to calculate. So sigma z equal to plus plus like this. So one first term, so this is plus t trace of that minus trace of minus minus t. But trace of this is just this equal to just plus element of t to the power L minus element of t to the power L. Okay, just because the matrix, okay. So let us see that how do you calculate this now. I am demanding that this will be 0 because of the symmetry, because the matrix is symmetry, but let us say calculate it. So this also I will do quickly. So t equal to e to the power beta plus sigma z e to the power minus beta. Okay, because this part which is called identity, as Sanjeev pointed out. So identity and sigma z of course commute. So eigenvectors of sigma z will be the eigenvectors. And what are the eigenvectors of sigma z? So this eigenvalue will be just sigma z is plus minus 1. So the eigenvalue lambda plus minus equal to e to the power beta and eigenvalues of this, because that basis. So plus minus e to the power minus beta, and corresponding eigenvector plus minus are just the eigenvectors of sigma z. So this is 1 plus minus 1 by square root of 2. Once you get the eigenvectors, you can construct the U matrix, right? So your U matrix equal to, you write E plus and E minus. Okay, so this equal to 1 by square root of 2, 1, 1, 1 minus 1. That is your U matrix. And T to the power L equal to U d to the power L U inverse. So this is 1, 1, 1 minus 1 half into d to the power L is lambda plus to the power L lambda minus to the power L 0, 0 into 1, 1, 1 minus 1. Okay, and if you multiply, just trust me, I remember. I mean, so many times I've done. So this equal to lambda plus to the power L plus lambda minus to the power L, lambda plus to the power L minus lambda minus to the power L, lambda plus to the power L plus minus lambda minus to the power L, lambda plus to the power L plus lambda minus to the power L, whole thing divided by 2. Okay, a check is the trace of t to the power L is lambda plus to the power L plus lambda minus to the power L. It has to, right? So you can calculate this. This plus that is twice this, half cancels out. So that is that's okay. Okay. So for this is true for any n. Okay. So I'm calling it L, but for any L this is true. So given t equal to this, let me write it again somewhere. I'll take it out. So t, okay. For Ising model, z equal to trace of t to the power L and t equal to e to the power beta plus e to the power minus beta sigma z, and eigenvalue equal to e to the power beta plus minus e to the power minus beta, e plus minus equal to 1 plus minus 1 by square root of 2, and t to the power n is lambda plus to the power n plus lambda minus to the power n, lambda plus to the power n minus lambda minus to the power n, and this goes here, half. So these are the formulas, we get it. So why I am writing all that? Because any observable you can calculate it very quickly using these formulas. It's just matrix multiplication. I want you to calculate. By the way, what did you learn from magnetization is 0 here, right? For each side, SI expectation value is 0. So what we learned, first thing we calculate that SI expectation value equal to 0. Because t to the power plus plus is same thing as t to the power minus minus, t to the power L minus minus. So this minus this is 0 here, and you have calculated it, S3 expectation value is this, and this one is t to the power L plus plus minus t to the power L minus minus, and plus plus is same thing as minus minus, so it is identically 0 at all sides. That is the proof that 1D Ising model has no phase transition. There is no magnetization, there is no finite magnetization here. But this problem has diverging correlation length, so let us see that how it works out. Okay, so we want to calculate now expectation value of SI plus X expectation value. Can you write the formula wise what it should be? I will erase that. So you want to calculate the correlation function SI plus X expectation value minus SI expectation value SI plus X expectation value, and these ones are 0. So this I called G of X equal to that, but this one is 0, so I just erase that. Okay, so can I write as a formula? You start with sigma x because you have a ith place, but this is same thing as 1 and x, right? So all you have is that you start with sigma x into sigma x sigma z. First side you put a sigma z, and then in between there are t's, and then again I plus x you have a sigma z. So sigma z t to the power x as many t's, and then again a sigma z, because this one corresponds to first one, ith one, and this is I plus x one, you have a sigma z. So wherever, so you have a t thing, and wherever you want sigma z, you drop them, right? I mean that is the way. Is it okay? Or in other words, you have this S1, P, S1, S2, and S2, and here you have S2, if you call it here, and wherever I plus x you have all S2. So this sigma z will come only at the distances. Yes?
I can't follow why are you calculating the average of sigma z?
Average?
While calculating the correlation,
Huh.
why from where is the sigma z coming?
Anyone else has the same question? Everyone else understood? Okay, no. So, okay, let us see. So, what is the expectation value? Let us say S2 expectation value you want to calculate. How do you calculate it? Just you have S2, whatever your observable, times probability of a configuration, summation over all configuration. That's the way you calculate. And what is probability of configuration? You say that e to the power minus beta, S1, S2, like that, right? So, this one I am writing in a plus e to the power minus beta, that becomes plus beta. And this one I am writing it in a stylish way, S1, T, S2. The next element e to the power beta S2, S3 will be S2, T, S3. And then S2 average, you have S2 here. You want to calculate this. So this S2 goes here, right? So what you get is that this matrix element, so S2 times S2 times S2, summation over S2. I am demanding that this equal to sigma z. Can you calculate this? So S2 can be plus and minus, right? So then what will happen if this is plus, if it is plus, 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 which means that it is plus, 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 plus. And then when it is minus, then it is S2 minus. Sorry, minus, minus. And this element is what? This plus is 1, 0. And this is 0, 1, 1, 0. And again, this one is minus, this is 0, 1, and this is 0, 1. And you multiply this as a matrix, so this will be 1, 0, 0, minus 1 equal to sigma z. Fine? Okay. So wherever there is S, you drop a sigma z there. That's all you are doing, okay, in correlation functions. Okay, so Gx will be trace of sigma x, sigma z, t to the power x, sigma z, because in between you have only t's, and then t to the power l minus x divided by trace of t to the power l. Are you comfortable with this? Is it okay? Anybody has a doubt here? Because because this is, if you write amino, because amino, I don't mind explain it again here, because this is exactly I will keep doing next five classes. So better clarify it here. How to,
The eigenvectors of the T matrix,
huh.
same as the eigenvectors of the sigma z matrix.
Yes,
Sigma z matrix has eigenvectors 1, 0, and 0.
sigma z, sigma x. This is sigma x. If I wrote it wrongly, sigma z, sorry, sigma x. This is written wrongly. Right, I mean, because t is e to the power beta, e to the power minus beta, e to the power minus beta, e to the power beta. So this and this makes it I, this and this makes it sigma x. Yeah, mistake. Thank you. Anything? Okay. So this one you understand? And how to calculate this? Again, just sigma z, you can calculate, right, I don't know. So this is, at least, this is just a simple matrix multiplication, if nothing, right? You can calculate it. And details we will do it later. Huh? First you try calculating this, because t to the power x, you know what it is. Because here it is written, this formula. Put it x here. And t to the power l minus x, put it there. And you can calculate it. Hmm? T to the power I minus x? But then it is okay. But yeah, trace is cyclic, so you can always, doesn't matter where you start, call it always 1. You can always call it 1 within the trace, because in a ring, you don't have an identity of what you call 7. Whatever you're calling 7, you can always call it 1. Anything else? Okay, I think so t to the power l, so generally what you do is that, so if you want to, a simple way to calculate is that t to the power x is just u d u inverse, right? You can go to the diagonal basis. So t to the power x can be written as sigma x, t to the power x is u d to the power x u inverse, and then sigma z, and t to the power l minus x is u d to the power l minus x u inverse. This is our trace. This is what you want to calculate, right? And this one, you can u inverse, you can bring it here because of the property of this, cyclic property of trace. So then this sigma u inverse sigma x u, this one, sigma z, yes, sigma z u, u inverse sigma z u is just sigma z prime. It's a matrix in a different representation. So similarly here you get u inverse sigma z u. This is just sigma prime and d to the power l minus x. So as if you are changing the basis. So in a diagonal basis, this one, this thing can be directly written equal to this, equal to trace of sigma z prime d to the power x, sigma z prime d to the power l minus x. Okay, so denominator, we will drop it later. So this is just the numerator, divide by t to the power L, okay, trace of t to the power L equal to lambda plus to the power L plus lambda minus to the power L. So this is lambda plus to the power L whole into 1 plus lambda minus divided by lambda plus whole to the power L, and lambda minus, which is e to the power beta minus e to the power minus beta, is always smaller than lambda plus. So this is smaller, and to the power L, L goes to infinity is 0. So this is effectively lambda plus to the power L. So divided by lambda plus to the power L in the thermodynamic limit. Okay. And now d to the power x you know. Okay. So I'm just saying that this will be proportional to lambda minus by lambda plus to the power x in general. And there is a question on question number 5, you can calculate it for any operator. This is always proportional to lambda minus by lambda plus whole to the power x. It doesn't matter what the operator. Huh?
That's too small, I can't.
Okay. This is lambda minus here. So this equal to this sigma x, you go to a different basis. This is sigma z. Sigma z prime times t to the power x become d to the power x because you are using the basis on which is diagonal. This is d to the power L, again sigma z prime and d to the power L minus x. Okay. Is it visible now? Divided by lambda plus to the power L. And sigma z prime equal to u inverse sigma z u. That is the way the basis transformation happens on matrices. Okay. And now I'm just saying that what is the variable here. So this, if you want to write, so let us say sigma z prime. I don't care about what it is. This one is lambda plus to the power x, lambda minus to the power x 0 0. And another sigma z prime, another one here, lambda plus to the power L minus x, lambda minus to the power L minus x 0 0, divided by lambda plus to the power L. Right? So what I do now, this is trace is also there, and what I do, take this thing common, take this outside. So this will be lambda plus to the power L minus x. If you take it away, here it will remain 1. Here it is lambda minus by lambda plus to the power L minus x. L is large, so this quantity can be, the thermodynamic limit, this goes to 0. So this is lambda plus to the power L minus x, I take out, and then I will put trace sigma z prime, and then here it is lambda plus to the power x 0 0 lambda minus to the power x, and the next one is sigma z prime, and the next element here, this element is only one element here, just one here. 1 means 1 1. So I can write this matrix as 1 1 or plus plus element. 1 means in my standard basis is plus plus. Right? A matrix which is 1 here, 1 0 0 0 is just plus plus.
So,
here.
by the way, this eigenvalue lambda plus is here, by the way. Here.
Lambda plus is?
Yeah, lambda plus is cos of beta, right? Beta j.
What is the eigenvalues of sigma x? Hello? Who is asking?
Yeah, here.
Ah,
Yeah.
What is the eigenvalue of sigma x?
Plus minus 1.
Yes. So if you have I,
No, I'm talking
to the
about the
power-
eigenvalues of t.
wait a minute, t equal to I e to the power beta plus sigma x e to the power minus beta, right? If eigenvalue, these two matrices commute. If sigma x is plus minus 1, it will be just e to the power beta plus minus e to the power minus beta, no?
Yeah, so one will be cos and the other is sine, right? The hyperbolic, I mean.
Of course, yeah. Say it correctly, yeah.
Yeah.
Twice also a factor.
Yeah, 2 cos.
But I mean, yeah, that's a name, but I mean, what do you gain by saying that?
No, what I'm trying to understand is like, how did you replace the bottom part, like the partition function to the lambda plus to the L? You replace the partition function by the lambda plus to the L, right? And you probably said that the large L limit, only one of the eigenvalue is bigger or something. I don't know.
I don't understand the question, but let me.
What is the
are you-
partition function? I mean, can you?
Is
just-
it okay here? Is it okay here?
Yeah.
Okay. So next what you do is that go to a basis change. This becomes sigma prime, this becomes sigma prime. Go to a basis where T is diagonal. This becomes a diagonal matrix. Is it correct?
No, I just have this doubt that what is the...
No, but this is correct.
This is correct completely.
I'm allowing you. So this one, denominator, I want to calculate it 1 by lambda plus to the power L. And sigma z prime d to the power x. What is d to the power x?
But you again, my main question is how are you replacing the bottom part as lambda plus to the L? That's what my question is.
T to the power L equal to lambda plus to the power L plus lambda minus to the power L equal to lambda plus to the power L whole into 1 plus lambda minus by lambda plus to the power L. So lambda minus is smaller than lambda plus. This ratio is smaller than 1. To the power L goes to infinity is 0.
Oh yeah, sine hyperbolic. Sorry, my mistake.
Okay. Okay, I forgot what I was saying. So sigma z is some sigma z and d to the power x is lambda plus to the power x, lambda minus to the power x, 0, 0. And another sigma z is here. And here it is lambda plus to the power L minus x, lambda minus to the power L minus x, 0, 0. This was there. Okay. So what I try to do is that I take this one common. Then this is lambda minus by lambda plus whole to the power L minus x, 1. And lambda plus to the power L minus x, I take it out. Okay. So this is a trace here. And divide by lambda plus to the power L. That also goes away. Right. So this lambda plus to the power L goes away. So if I take it out, then this will be whole divided by lambda plus to the power x. Okay. Then if I lambda 1 divided by lambda plus to the power x, that's what remains, lambda plus to the power x. So if I multiply it here, this will be lambda plus to the power x divided by lambda plus to the power x. This will be 1, and this is lambda minus by lambda plus whole to the power x. And sigma z prime, this sigma z prime, those are simple matrices. So sigma z prime equal to u du inverse. U, which is 1, 1, 1 minus 1, sigma z, which is 1 minus 1, 0, 0, and inverse is same thing, 1, 1, 1 minus 1. And there is a half here. Okay, so this is some constant matrices. So the x dependence comes only 1 lambda minus by lambda plus whole to the power x. This part is clear? Yeah, if you have doubt here again. So it doesn't matter what is the operator, right? It is eventually it will come as lambda minus by lambda plus to the power x. Okay, so sometimes the transfer matrix can be bigger than 2-dimensional. So then the correlation function in the general matrix lambda x equal to lambda like in lambda 2 divided by lambda 1 to the power x plus lambda 3 divided by lambda 1 to the power x, assuming the lambda 1 is largest. Okay, so that's a question which is there in question number 5. Try to solve it. Okay. This part is clear. At least for Ising model, this part is clear, right? Lambda minus by lambda plus to the power x. So the correlation function, now we will go to this. So g of x equal to lambda minus, which is e to the power beta minus e to the power minus beta divided by e to the power beta plus e to the power minus beta whole to the power x. So this equal to 10 hyperbolic beta to the power x. Okay. This is just 10 hyperbolic beta whole to the power x. So now let us see that what happens. So this gx can be written as e to the power minus x. So something to the power x can be written as e to the power x log of this, log of 10 hyperbolic beta. So it can be written as e to the power minus x by xi, where xi inverse equal to log of lambda minus by lambda plus. Okay, or let us write xi equal to 1 divided by log of lambda minus by lambda plus. This part is clear? So what I am writing is that gx equal to lambda minus by lambda plus whole to the power x. So a to the power x is e to the power log a into x. So this one can be written as mode of course. So that lambda minus by lambda plus is negative, lambda minus by lambda plus is less than 1. So log of that is negative. So I will put a negative sign here. Okay. So that equal to e to the power minus log of lambda minus by lambda plus mode times x. Gx equal to lambda minus by lambda plus to the power x is e to the power minus this into x. So if I write it equal to e to the power minus x by xi, then xi will be this. Okay, so you can see that the correlation length diverges when lambda minus becomes lambda plus, because log of 1 is 0, so this will diverge. And that happens if you look at your eigenvalue lambda minus and lambda plus, that happens when this becomes 0, right? E to the power beta equal to 0. So when temperature is 0, so 0 temperature beta is infinity, so this part is 0, so both eigenvalues touch. Okay, so that is the time when eigenvalue crossing, wherever eigenvalue crossing happens, that is the place where the correlation thing diverges, and it is at t equal to 0. So Ising model correlation length diverges at t equal to 0. Okay, I think I will. This is a short summary according to me. It's too long for but anyway. Okay, you have questions here?
Sir, I understood the mathematical part that you have done.
Yes.
Just repeat the conclusion that you made using about this correlation length, the last statement that you just said.
Correlation length.
Yeah.
The correlation length is this, right? When does it go to when at what place? I mean, what is the condition at which xi goes to infinity?
So when lambda minus equal to lambda.
Yes. When does that happen? So lambda minus is e to the power beta, lambda plus minus equal to e to the power beta plus minus e to the power minus beta. When does this happen? When this plus is same as minus, when this is 0. When that happens? At t equal to 0. That's what I'm saying. So at t equal to 0, this correlation length diverges. Okay. So when the eigenvalue crossing, wherever the eigenvalue crossing happens, that's the one. That's where the correlation length diverges, and that is the criteria for phase transition also. Okay. So in here, except at t equal to 0, the eigenvalues never touch each other. So you cannot have a phase transition in one dimension. So for any finite dimensional matrix, you cannot have a phase transition. Finite dimensional transfer matrix, not only Ising model. So this is generally called a non-existence theorem. And again, there is another question which you can with that. So try to solve them. This is. No, I think too much of algebra is too not good on the blackboard, I think. So maybe, Yes. Negative. That's the reason I put a mode and put a minus sign. Did I put or did I not? Yeah, minus log of lambda minus. That's the reason I just to explicitly say that that is a negative quantity. Fine? Okay, great. So now what I want to do, about the dynamics. So how many of you have simulated 1D Ising model using Monte Carlo? Not simulated 1D Ising model using Monte Carlo simulations or something. Okay. Oh, so then many people who do not know about the dynamics, right? I mean, so question is that when you think that it is so steady, when you talk of statistical mechanics, it is called mechanics, right? I mean, I'm asking you a question, but all other mechanics like quantum mechanics, classical mechanics, whatever mechanics, they have a time somewhere, right? But in the whole book of statistical mechanics, there is nowhere time. There is no evolution. Where does the evolution go? So what are you talking about mechanics in statistical mechanics, right? So all you are talking about is just the steady state, right? I mean, all you are saying is that when the system flow goes to a stationary state, you are describing only the stationary state, what happens in the stationary state. You never discuss about how the system goes to the stationary state, okay? So let us discuss that, the dynamics of Ising model. But then actually equally, so basically this is Ising model is an example. But generally what I'm talking about, what is the equilibrium dynamics? So whenever you talk about Hamiltonian and when you say the system is in temperature T, what kind of dynamics can lead any arbitrary configuration to what you call the equilibrium state? Okay. So the equilibrium state, you know, this is the equilibrium dynamics. Okay, it's general equilibrium dynamics. So what are the conditions you need, and how should you define equilibrium dynamics? Okay, so you have a Hamiltonian which is given, or an energy function which is given. I'm taking eigenmodel example. So probability of a configuration. Achha, by the way, that is e to the power minus beta E of SI, or the Hamiltonian energy function, divided by Z. So, and configuration is also, I can call it SI. Okay. So this is the probability which is given. And what I want to know is that if the system is in equilibrium there is a condition called detail balance condition. The detail balance is satisfied in equilibrium. What does it mean? So the description of a stochastic system is given by, in terms of configurations, configuration C1, C2, C3, C4, some configurations. And all what happens in dynamics is that the system moves from one configuration to the other. So for example, if you take an Ising model, just two sides, let's say two sides. So how many configurations are there? 4. So it is plus plus, plus minus, minus plus, minus minus. So these are the 4 configurations. Okay. So whenever, if you think that the system is doing some dynamics, the system is jumping from one configuration to another configuration. So you can call it, let us say C1, C2, C3, C4. These configurations, let us say in 2D Ising model, these are C1, C2, C3, C4. So what can happen at most? Your description is that, you know, from this configuration it can go to this configuration. So you can write some rates. You don't know what rates, so you can write this to that with rate R1, say like 1, 2. So R1 going to 2. Let us say call W1 going to 2, and this one W, let us say, what is that? 2 going to 3, and this to that is W3 going to 4, and this to that is W4 going to 1. You can write, I mean, you know, maybe you can write the other way also, like, you know, so if you want to put it here, you can define whatever dynamics. So from here to here, it is W1 going to 4. If you want to write, you can write any dynamics. And there are 4 configurations. But the point is that with time, if you want to watch, the system is only jumping from one configuration to the other, because the system has only 4 configurations. So if the rates are given, then you don't have, if the rates are known, then the system is doing something according to the rates. So now your question is whether the system will eventually go to equilibrium steady state. So if you put arbitrary rates, it will not go to the steady state, because in the steady state you want this rate should be satisfied. So for example, if it is plus plus, the energy is two spins, just minus S1, S2. So this one is minus 1. So here energy is minus 1. So e to the power minus 1, this would be e to the power minus 1, e to the power 1, e to the power 1, up to normalization constant. That's what should happen. But will it do that? If you write arbitrarily things, it will not go there, right? So what you want to write a dynamics which will take the system to generate this configuration. Eventually t goes to infinity, generate this configuration. So so what you want is that, so rates WC to C prime should be such the detail balance condition should be satisfied. Probability of WC to C prime must be same as WC prime to C P of C prime. So what does it mean? That there is a configuration C and there is a configuration C prime. This flux must balance with this flux. C to C prime, so WC prime, C to C prime, and this one is WC prime to C. This must be satisfied. So this implies that WC to C prime divided by WC prime to C, C to C prime to C equal to P of C prime divided by P of C. But P of C you want in equilibrium is in the steady state is e to the power minus beta this. So this will be e to the power minus beta E of C prime, and here is e to the power minus beta E of C, so minus E of C. So ratio of rate should be e to the power minus beta delta E, change in energy, right? So your delta E is E of target minus E now. So you are in some configuration, wherever you are, that configuration has some energy. You are targeting to go some energy. So the difference between target and this is delta E, and the ratio of rates has to be this. The ratio of these rates must satisfy e to the power minus beta delta E. Okay? So keeping this in mind, you still have two rates, and you can devise, you have two rates, right? Two of the rates has to be specified, and you have one condition. So you still have choices. Okay? A simple choice is that, so if you are going to a lower configurations, going to lower energy, rate is 1. Going to higher energy, rate is higher e to the power minus beta delta E. Delta E is now positive. So this is here, delta E is negative, and this is delta E is positive. Right? Going to higher basically means that the target has more higher energy. Okay? So that is what you call Monte Carlo dynamics, delta E greater than 0. Okay? So in general, so the rate in one line is that minimum of 1 e to the power minus beta delta E. That is the rate at which transition occurs. Delta E is the rate, delta E is the change in energy from the target, and delta E equal to E target minus E now. Okay? So now these dynamics actually satisfy detailed balance. You can check. Okay, so these dynamics, so this is a homework, I think I don't do it now. So you can check that these dynamics actually satisfy detailed balance, because ratio is either, so suppose one configuration C and C prime, right? So now if you are, let us say C prime is bigger, then if it is higher energy, then this one is e to the power minus beta delta E, and this one is 1. Because if it is higher, while coming back, this has to be lower. I mean, because this is lower energy, coming back to a lower energy. So this rate has to be 1. So the ratio is always e to the power beta delta E. Okay? So that is the way the detailed balance condition is satisfied. And what I am trying to do is that, let us try to write these rates once.
So the detailed balance condition to the condition on rate.
Detailed balance condition, we use a detailed balance condition. So okay. So what we, you have a Hamiltonian or energy, right? So given an energy, you want to figure out what are the rates, and you do not know the dynamics. All you know is that once it reaches the stationary state or the equilibrium state, detailed balance is violated. Detailed balance is satisfied there. Okay? So what you are trying to do is that on the way, every step you want to make sure that the detailed balance is satisfied. It is not required. So detailed balance, the condition, the way you are devising the dynamics is not the efficient dynamics, but it's a sure shot dynamics which will take you to equilibrium for sure. Okay? How to make it efficient is a different chapter. Okay? So this is a detailed balance is an unnecessary condition on the dynamics, makes it slow. But this is all you want is that it's a guaranteed state, guaranteed thing. Okay? You want to reach equilibrium state. So all you want is that you start with arbitrary configuration, let's say all spins up, and at a given temperature T, the system some spins should flip. So how do you know that it will generate configurations of a specific weight, right? Specific probability. This, because in 2 to the power L configurations, each of them has to be generated with a specific probability, okay? And that's a method to do it. Okay. So that's what is detailed balance, and what I'm trying to do is that as an exercise for now, one time to write this this one. So can you do it for this, because that is easier. I will do this. So let us say this is plus plus, plus minus, minus plus, minus minus. So the energies of this equal to, this one is energy what? Plus 1. This is 1. So this is minus 1, this is minus 1, this is minus 1. These are the energies. Okay? Sorry. I'll make it bigger. Sorry. So this one is plus plus, the state. This is plus minus, minus plus, minus minus. Energy is minus 1, and E is minus 1. E equal to plus 1, E equal to plus 1. And detail, well, if you want to write a rates from this configuration to this configuration, what will be the rate? I mean, you can also join from this to that, but this to that require 2 spin flip, right? So you want to restrict single spin flip dynamics. Can you tell me what are the rates from here to here? So I will name it also. This configuration is 1, this is 2, this is 3, this is 4. So 1 to 2, what is this rate? Energy goes up or down? Up. So what should be the rate? The change e to the power minus beta, what is that? E to the power minus 2 beta. And what is this way? 1. And what are these? Plus 1 to minus 1, 1. And what is that? E to the power minus 2 beta. So e to the power minus 2 beta, I will write it q, is e to the power minus 2 beta. So I call it q. So this is q and 1. And from here to here, again this one is 1 and this one is q. From here to here, this one is 1, this one is q. And q is less than 1, so rate is lesser. So higher energy is punished. Okay? So now if the system actually does this, is a Markov process, right? Huh? So yeah, I want to write. Huh?
Sorry, what is the reason for considering only single spin dynamics?
We write, for the time being, we do the single spin dynamics, but we can do the multiple dynamics also. This is just an example I'm giving. You can put the other rates also. So when you go to, okay, let me address this. So if you have a L side configurations, right? You want to think of a dynamics. Dynamics basically means that one configuration, it can go to one other configuration, but you can flip spins, 1 spin, 2 spin, 5 spin, 75 spins. You can, whichever way you want, you can do it. So now question is that if you want to assure that it visits all configurations, so that the minimum energy configuration or the minimum entropy configuration is achieved, that you have to make sure that all configurations are visited. So if you make your dynamics, let us say 25 spins flip at a time, then what will happen is that the energy will change by a big number. So in the energy space, you will jump big spaces, and you might miss the local minima sitting somewhere. So it is always, this single spin flip is assured that it is ergodic, and it actually visit all configurations to find the minimum. And if you are using 2 spins or multi-spins, you have to make sure beginning that the dynamics, whatever you're using, is ergodic. And yeah. Why? There is a temperature sitting there. There is a temperature. So why should T equal to 0, the system is in a ground state? Let us look at this. So then let us say that the system has 4 or 5 energy configurations, energy E1, E2, E3, and all of them are smaller. So e to the power minus beta E1, so P1 is e to the power minus beta E1 is e to the power beta minus beta E1 plus e to the power minus beta E2 plus e to the power minus beta E3. This is this. And P2 is e to the power minus beta E2 divided by same thing. Now, when T goes to 0, you can see, I'm asking you, who asked me? Yeah, I'll also ask you back. So now if t goes to 0, then this is infinity, right? Beta is infinity. Then this is 0, this is 0, this is 0, this is 0. So this is 0, this is also. So how is it possible that all probabilities become 0, na? Because e to the power minus beta e1 is 0, e to the power minus beta e2 is 0, e to the power minus beta e3 is 0. So how is it possible that the system has 3 energies and all energies are 0 when t goes to 0? So that is not true, because t goes to 0. I mean, you can see that this you can neglect, this you can neglect, right? Because this is 0, you cannot neglect this. So this probability will be 1. Everything else, this one will be e to the power minus beta e1. So this will be 0, but this one will be 1. So the ground state with the lowest energy occurs with probability 1 only when t equal to 0. Okay. Any other question? Okay, ask. No problem. No, ask, please.
Slightly pathological when temperature.
Oh, then later. No, pathological, we don't take it now. Yeah. Okay. So can you write the dynamics for this? So now let us think of an ensemble. Okay, ensemble basically means this is a system with different configurations, and you think that there are many such systems, some millions or whatever, n such system, n can be large. So let us say n systems, some of them n1, some of them n2, some of them n3, some of them n4. This is the ensemble you have created. Okay. So the change, how does the change occur if this is the rate? Let us say you want to write the change occurs in 1. How does it occur? Can you write for this? Currently you have n1, n2, n3 and n4. This plus equal to n. You have n systems like this, and you have n1 of type 1, n2 is type 2, n3 is type 4, n4 is type 4. Okay? So all you want to know is that this is a time t. So currently you have n1t, and we want to know in delta t time what will be n1t plus delta t. N is the number of plus. You have a system, right? So you have copies. N such copies of the system. This one is made to be plus, this one is minus, plus, minus, minus, product. Each of them has 2 spins and many copies. You count how many of them are plus. That is n1. How many of them are plus? Let us call it n plus, then I don't have to n plus. Okay? You want to calculate how many n plus at t, you know. You want to calculate n plus at t plus delta t. Can you calculate this? So those which are at n, those which are here, they will also lose because of this. Na? So you have n1 t plus delta t is n1 of t, first thing, whatever was there. So now gain will happen from here, right? N3. So plus those which are at 3 means N3, and they will come to W3 to 1. This I am calling it 1, actually better. N1T, N3, W3 to 1. This is the rate. So basically those which are at N3 with probability W3 to 1 delta T. If rate is whatever rate times delta T is the probability, because rate is T inverse. Okay. So this is the probability. So this is the gain from N3. This mastery question was taught now. Yeah. Okay. So plus N3 W3 to 1. Can you just write complete this? What else? What are the other gain terms? One comes from N2. So plus N2 W2 to 1 delta T, and minus N1 W1 to what? 1 to 2 delta T minus N1 W1 to 3 delta T. Right? So now what you do is that you subtract this N1T minus N1 delta T equal to this. And this delta T, now everywhere there is a delta T, you take it out. drop it here, and total number also you divide everywhere. So when you divide, you don't call it n anymore, you call it probability, because this is the fraction of systems in that ensemble, you call it probability. So this will be dp by dt, if I write dp1 by dt equal to this one n3 p3 w3 to 1 plus p2 w2 to 1 minus p1 w1 to 2 minus p1 w 1 to 3, right? Is it? It's fine, right? So now this one also we will have a matrix, same thing, similar thing for, so this is, I call it P1 when n goes to infinity and delta t goes to 0. So that is the one, this becomes dt and this becomes P1, probability. Because the fraction of systems in configuration this is called probability in n goes to infinity limit. Okay, so this is this one. So what I do now, I think I'm doing very slow. The probability.
You have written P3 W3 to 1. So you are writing n into delta t to the P here.
It's the probability of a configuration and the probability of a movement.
Yeah. So, oh, you are writing,
Okay.
You have changed it. Yeah. Right.
So okay, if there is a rate in delta t time, the number of events rate times delta t, that is the number of events happens in delta t time, and which n1 of them it will just pass away. So this is the equation, right? So for this one can write Can you write now the, so this is for P1. So similarly you can write it for P2, right? So let us write an equation for this. So d by dt of P1, P2, P3, P4 okay, P1, P2, P3, P4. So P3, where does it appear? W3 to 1. W3 to 1 P3, right? W3 to, so here we will write, this is the place for 1, 2, 3, 4. This is for P3, W3 to 1, P3, right? I mean, if you multiply dP1 by dt, this one times P3, and P2 times W2 to 1, so here W2 to 1, and minus P1, W1 to 2, W1 to 3. So here minus W2 to 1, 1 to 2, plus W1 to 3. And I insist that you, for this particular dynamics which you write here, you fill it up. Okay? So from this, what I wanted to say is that, so W2 to 1, in terms of matrix element, if you call this matrix is M, then M, this is M12 equal to W2 to 1. Okay? So Mij in general equal to Wj to I, and Mii equal to Wi to j summation over j and with a minus sign. This is a loss term. So this is the diagonal element. I not equal to j, I equal to j. So this is the matrix element. And from here, you can say that, right, the column sum of this matrix is 0. I think it is always useful to complete this equation. Can you complete this? Can you write in your notebook just this 4 by 4 matrix you complete? I think it will. Yeah, I think I will. I will leave it as exercise, you can do it later, and convince yourself that if you complete this, the column sum of this matrix is 0. Okay, because what happens is that every time from a configuration, so if you have some C1, some C2, when you take this arrow, for this one it is a, this rate is some W, for this configuration it is a loss, for this configuration it is a gain. So W once appear as minus, as a minus W somewhere, plus W somewhere, so the sum will be, it will cancel out. So every rate, every time something happens, some configuration loses, some other configuration gains with the same rate. Okay, so that is the way the column sum is 0. So this is the equation, this is the master equation, which you write is dp by dt equal to 0. P is a vector. So dp by dt equal to m into p. And we have seen that determinant of m equal to 0 because the column sum is 0. Right? So if you want a probability evolving like that, going to a steady state, in the steady state the probability should not depend on time, which means that dp by dt has to be 0. So the steady state that means that dp by dt equal to 0 equal to m times p. So m times p, mp equal to 0. So steady state basically means that m times p equal to 0. So I'll write it in a matrix notation. So I'll write it m times p equal to 0 times p. So it looks like p, if there is a steady state, so for some p star, right? I mean, if there is a steady state, it represented by p star, that m p star equal to 0 p star. So all you are looking for, the steady state basically means that the eigenvector of the matrix M corresponding to the 0 eigenvalue, right eigenvector. Right eigenvector of M corresponding to 0 eigenvalue. Okay? And the 0 eigenvalue is guaranteed because the determinant of the matrix is 0, which means that at least there has to be at least one 0 eigenvalue. But why it is unique? So I think, actually there is something called Perron-Frobenius theorem. That is again a question which I there is a question there. So you can prove that not only that, 0 is not that 0 eigenvalue exists. And this is the largest eigenvalue in terms of the real part. Okay, so the all other eigenvalue, the real part of all other eigenvalues, lambda is less than 0. Okay, so okay. So it is up to 4 o'clock. Okay, so then I think I will not be able to cover the whatever I meant to do, but I think I will continue with this. So I'll rather continue with this. So what we know is that for every stochastic process like this, we have an equation called a master equation. Okay, and the master equation has some gain terms and some loss terms, and these elements will tell you that where it is going, like W2 to 1. So if it is 1, this way you have to look for, and the column sum is 0. Okay. So the other one is that dp by dt equal to mp. That's this equation. With the I, it's like a Schrodinger equation, right? I mean, this is just how a vector evolves. Only difference is that M, that could be, no, that can, why? Steady state has to be unique, right? Steady state, there are two things. If there is a steady state in the system, that the steady state is unique, and the steady state, and it should be independent of the initial conditions, right? I mean, so basically, so steady basically means the water, a glass of water here, and you should not know whether it has come from a refrigerator previous day or it has come from a hot or boiling water. So initial condition, it doesn't matter. Okay, so it should be initial. So that is the thing we have to prove, that this should be starting from any initial condition, it goes to the same stationary state, steady state. Okay. What is the solution of this? Formal solution. So the solution of this can be written as Pt equal to e to the power t times m p0, p at t equal to 0, right? It's fine, right? This is just like, yeah. And then if you write, so the way to write it, p of 0, if you write it, this is a vector, you can write it eigenvectors of m. So m of ei equal to lambda I ei if there is a right eigenvectors, and lambda 0 equal to 0 is less than real of lambda 1, less than real of lambda 2, is greater than real of lambda 2, real of lambda 3. I'm saying that all other, the real part is negative. So then p of 0 can be expanded in this eigenvalue, just ci ei. So then if you put here e to the power tm p0, so this will be summation over I ci e to the power t times lambda I ei. That's the solution. And just because in t, if you take t goes to infinity, then only the 0 eigenvector survives. Everything else has a negative part here, and t goes to infinity, the vanishes. Is it clear? So that is the meaning that irrespective of the initial condition, if you evolve the system for sufficiently long, you reach the largest eigenvector. Actually, that is true about any matrix. So if you just operate this, is it clear? Because all the eigenvalues are negative, so minus t will be there. T goes to infinity, this real part, it will go to 0. And one of the eigenvalue is 0, so that will give you E0. So this limit of this, so if I take limit t goes to infinity, so this will be proportional to E0. Okay? So what is, just one second because you're not done. So what I have not proven is that why the real part is negative. That proof, I leave it to you. That is Perron-Frobenius theorem. And someone also asked that can you have a two zero eigenvectors. I can give you trivial examples which will have two stationary states. So let us say that there is this plus plus, these things are called, there is a Hamiltonian which is S is minus S1 S2 minus sigma 1 sigma 2. This is the Hamiltonian. Okay? But there is no connection between S and sigma, so there are two independent systems. Right? I mean, so the flipping, so they will not go from one configuration to the other. So basically there will be two independent, so in the phase in this connecting space, you have one connections like that and one connection like that, and there is no connection from here to here. If that happens, I mean, I don't know whether I give a correct example, but if the dynamics is that some C1, C2, C3, C4, C5, C6, C7, C8, they are connected some way, but there is no connection between this and that, then you will get a 0 from here, can get a 0 from here, right? So if for this, the matrix which you get will be reducible, okay? So what I have is that generally the theorem is that if M is irreducible, which means that the corresponding space is ergodic, then you have a unique stationary state. Okay, so this is a property of irreducible matrices. More we can discuss in the tutorial. Okay, so if the matrix is irreducible, which means that everything is connected to everything, then the system has only one unique stationary state. Otherwise, yeah, you can have multiple ones, but those are odd problems. Okay, and what I have not proven is that why other eigenvalues are negative. Other thing which you want to know is that E0, but E0 is a probability, right? So now E0 is the stationary state probability, which means that each element has to be positive. So the largest eigenvector has to be positive also. So all these properties are given by the Perron-Frobenius theorem, and I've given a link, a small proof, 2-page proof of Perron-Frobenius theorem, or if you want in a tutorial, we can discuss that also. Okay, I stop here, and next time I will ask you to write the master. So homework, this if you do, it will be useful. So 3 sites, you take 3 sites, okay, just 3 sites in a periodic system, and take Ising model and write M. This matrix M you write, and yeah, we will start there. Okay, and you will see how matrix product answers help. Okay.
Okay, so we'll meet again after at 4:30 for the second lecture by Prabha.
Should I switch off?